This is a presentation of our work, Critical Features Tracking on Triangulated Irregular Networks by a Scale-Space Method. I'm Haoan Feng from University of Maryland. First of all, let's start with some background. Critical features are features consist of representative points together with their relations and regions of influence, where the surface topology undergoes significant changes. For terrain surface analysis, which is the main focus of our work, critical points are locations where gradient of the function vanishes. That's to say, critical point contains peak, saddles, and pits of the terrain. Understanding critical points and further analyzing their relative importance give us a better understanding of the topological structure of a surface, which is crucial in several downstream applications, such as cartography, nautical charting, and land use planning. Among many analytical methods, scale space is a widely used framework in the field of image processing and analysis. Similarly to the human visual system, a scale space method processes data at different levels of details. It allows us to focus on prominent features at rough scales and relate them with complex details in finer scales. Tracking critical points across scales captures the evolution of features of a surface, and it helps us understand the deep structure of this surface. We use the term lifespan to represent the number of scales that a critical point survives. It indicates the relative significance of critical points in the data's underlying structure. Here is an animation illustration. The input scalar function gradually changes with respect to the scale, which is also termed as time step here. Two peaks with different prominence change differently. The less prominent peak merges with its neighboring saddle at a certain time step, and the more prominent one survives to the last time step. Now let's see a previous work by Luigi Rocca, which inspires our work. It makes use of a scale space method to analyze the deep structure. The input is a digital elevation model in raster format. A scale space is constructed by repeatedly applying a Gaussian smoothing operation on this regular grid. Each grid cell is divided into two triangles to produce a piecewise linear approximation of the terrain surface, as shown in the corner left image. Then critical points are identified by inspecting the relative elevation to their direct neighbors on this triangle mesh. As shown in this figure on the right, each vertex in this mesh has 6 neighbors. Besides a regular vertex, we will have 4 types of critical points: minimum, maximum, saddle, and monkey saddle, which appears only in the discrete setting. To track critical points, a virtually continuous scale space assumption is made. It says that between neighboring scale layers, vertex elevation changes linearly. As you can see in this 1D toy example, during the scale changes from Si to Si plus 1, relative elevation between Vm and Vn swapped. By the linear assumption of this scale space, we can calculate the time step at which this edge between Vm and Vn flipped, at I plus delta. Then, tracking all the edge flipping events in chronological order, we are able to track each individual critical point transition deterministically. However, this method is limited to the raster format input. Well, nowadays, point cloud data is more accurate and widely available. Moreover, if we convert a point cloud to raster format and then triangulate the grid, the preset edge connection on this regular grid affects the classification of critical points as shown in this figure. For regular grid, there is a trade-off between accuracy and computation burden. It increases quadratically with the resolution of the grid. Therefore, it is necessary to work with point cloud data directly. That's to say, we need a scale space method for teams. Adaptive resolution of a team allows for accurate tracking with lower cost. Moreover, teams can naturally handle data with irregular boundary geometry, such as bathymetric data. Here is a visual comparison of the graded DEM and team with similar number of vertices. As can be seen here, team preserves the mountain details such as peaks and ridges better than graded DEM. The figure on the left looks pretty smooth. Here is an animation comparison. Critical points are annotated as colored balls, and we also show the underlying wireframe of both representations. Again, for a team, adaptive resolution allows allocating more vertices in the region of interest, while reducing vertices in simple regions such as plateaus. The main challenges of migrating from regular grid to teams are mainly twofold. First, the construction of a scale space on a team, and then the tracking of critical points with unbounded neighboring configurations. We will see in details next. First of all, point cloud data are usually unevenly distributed. Furthest point sampling method is a widely used downsampling approach to get a subset of points which is evenly distributed. To take advantage of team's adaptive resolution, we propose this patch-based FPS method that samples different number of points based on the local complexity level. Point cloud is divided into subregions on the XY plane, and we measure the complexity by the estimated curvature of the patch. As shown here, the team generated from original point cloud is on the left. Our PFBS method result is on the lower right corner. Compared to other downsampling methods, it allocates more points in complex regions with the same total number of vertices. Here is another example of real-world terrain. The hue shade of this terrain is shown on the left. Team and graded DEM wireframe wheel are shown on the right. As you can see, with same number of vertices, team's adaptive resolution allows us to allocate more vertices in the mountainous regions than the plateau regions. With the preprocessed point cloud, Delaunay triangulation is applied, and the sliver triangles on the boundary are filtered out by alpha shape. The resulting team is then stored in a terrain tree, which is an efficient spatial data structure for large triangulated 2.5D surfaces. Alpha shape is derived from a Delaunay triangulation result. For each triangle cell, its circumradius is calculated and compared to a precise threshold, which help us filtering out sliver triangles on the boundary. Gaussian smoothing operation is formulated as a matrix vector multiplication. Vertex elevations are stored in a vector, and the transition matrix is used to update the elevation of each vertex. This transition matrix is based on the adjacency matrix, which contains the edge connection information of the team. And based on the edge lengths, elements in the transition matrices are derived. However, this naive adaptation of Gaussian smoothing from raster data to a team does not perform well. As you can see, contour lines on the right indicate the smoothing does not work as expected. Notice that different from a regular grid, neighboring vertices on a team are distributed unevenly. We propose to reweight their contributions to the smoothing operation based on the angle each neighboring vertex shares. And a virtual neighbor is introduced for each edge longer than a precise threshold to avoid its contribution vanishes. Because Gaussian smoothing is inverse quadratic to the edge length. For the neighboring vertex V1, V1 prime is introduced, interpolated on the edge between V and V1, and keep updated during the transition. With this improvement, our team smoothing result is aligned with the image smoothing result. Now, a scale space is defined on a team. In this scale space, critical points are tracked by processing edge flip events in chronological order. critical point transitions are classified into three categories: displacement, that a critical point moves along the flipping edge; collapse, that two critical points cancel each other, leaving two regular vertices, such as shown in this example; and lastly, the appearance is an opposite case of collapse. By the Poincare-Hopf index theorem, collapse or appearance can only happen to critical points in pairs of the form maximum saddle or minimum saddle pair. Here is the transition table from a regular grid used in previous work. Remember, each vertex in a regular mesh has 6 neighbors. You will have up to monkey saddle cases during analyzing the critical point transitions. In the discrete setting, k-fold saddles appears as we saw in the previous grid-based method on a tin because the number of direct neighbors is not fixed. When k equals to 1, you have a simple saddle. K equals to 2, a monkey saddle appears, and this k number can go greater than 2 in the tin from real-world point cloud dataset. In our method, each k-fold saddle is treated as k simple saddles overlapping at location of current vertex. In case of regular meshes, you will have 1 and 2-fold saddle, which makes it easy to consider all possible transition cases as shown. Well, for tins, we have to further consider each saddle separately to multiple transitions when an edge flip happens. We conduct an experimental comparison with the previous grid-based method, and we will briefly go through this section here. Spot heights are used in topographical maps to indicate the local terrain elevation. Cartographers have developed design principles for the manual selection of spot height locations. In the experiment, we match critical maxima with spot heights in the datasets. Experiments are conducted on 3 different point cloud datasets of Switzerland. They are of various scales and topographical types. And as a binary classification problem, we evaluate the results based on the precision and recall rate, and also the F-beta score as formulated here. In addition, we also measure the average matching distance between maxima and spot heights. Compared to the grid-based method, our tin-based method results are more accurate in terms of matching. Especially, the average matching distance is much smaller. Here we zoom into 2 different regions in one of the datasets. As we can see, with the adaptive resolution, we allocate much more vertices in the mountain region where prominent critical points exist. And for the plateau region, we have a rough tin for insignificant critical points. We also compare the precision recall curve and F-beta score here. In both figures, critical points lifespan is used as a filtering threshold. As highlighted by these yellow rectangles, grid-based method cannot reach higher recall rate due to the resolution limit. In other words, denser sampling in the mountainous region improves the recall rate of critical points. And we also compare the performance of both methods when limit the size of triangle meshes. Here, tin-based method is less sensitive to the change of resolution than grid-based method. In a conclusion, we propose an efficient method of critical features tracking on a scale space defined on a tin. From an input point cloud, patch-based sampling and iterative Gaussian smoothing are applied to build this scale space on a tin. Then, taking advantage of tins, we are able to achieve more accurate results with less computational burden. Thank you, and this is the end of my presentation.